In the name of God, I'm Asghar Azizian, and in this course, we are going to learn how can we use HEC-RAS 1D model for inline structure modeling. Okay, as I told you in the previous sections, you can model or you can simulate hydraulic structures such as bridge, culverts, or dam in HEC-RAS 1D model. First of all, we want to focus on how can we model the bridge and their related settings and other important parameters. Okay, first of all, let's review or briefly review the numerical concepts of bridge modeling using HEC-RAS 1D. Okay, in order to bridge modeling or other related inline structure, first of all, you should define cross-section locations. For modeling every single structure, you need 4 cross-sections. Two of them are located in the upstream of the bridge or structure, and the 2 other are located in the downstream of bridge. Let me to show you a simple bridge. Okay, this is a plan figure of the location of cross sections. 4 and 3 located in the upper of the bridge, and the cross sections of 1 and 2 are located in the downstream of the bridge. Okay. Okay. This is a part of reference manual of a HEC-RAS model, and it says that the bridge routines utilize for user-defined cross sections in the computations of energy losses due to the structures. During the hydraulic computations, the program automatically formulates 2 additional cross section inside of the bridge structure. This is the plan of the location of cross section, and this is the channel profile and cross section locations. You can see 4 and 3 cross sections are located at the upstream of the cross section, and cross sections 1 and 2 are located in the downstream of the bridge. Okay. This reference manual says that cross section 1 is located sufficiently downstream from the structure so that the flow is not affected by the structure. For example, you can set the location of cross section 1 about 50 meter or 40 meter downstream of the bridge, or a little bit more than 50 meter. This distance should be determined by field investigation during high flows. However, it's generally not likely that a large event will occur during the scope of your project. Therefore, modeler must estimate this distance from known information. And it says you should go to the field and estimate the distance of this parameter. Okay, one of the most important parts of bridge or other structure modeling is the calculation of losses from the expansion and extension. In the table 5.1, there are different range of expansion ratios. For example, when the Manning roughness coefficient of a floodplain divided to Manning roughness of channel is equal to 1, for each B per B parameters, you can select a range of expansions. Okay, what's the B per capital B? It says that B per capital B is the ratio of the bridge opening width to the floodplain width. Okay, smaller b is the bridge opening and the capital B is the total floodplain width. And by dividing smaller b to capital B, you can estimate a range of expansion ratio and use in the HEC-RAS model. Okay. And okay, the cross section 2 is located a short distance downstream from the bridge. I recommended you to use, for example, 2 meter or 1 meter or maximum 3 meter to locate cross section 2. This cross section should represent the natural ground main channel and floodplain just downstream of the bridge or culvert. You can use smaller values for cross section 2. I mean, you can use dimensions about 10 meter, 20 meter, or higher values. You should locate this cross section near the downstream of the cross section. Cross section 3 should be located a short distance upstream from the bridge. The distance between cross section 3 and the bridge should reflect the length required for abrupt acceleration and contraction of the fluid that occurs in the immediate area of the opening. And in this case, you should use a distance about 2 or 3 or 1 meter from the upper of cross section. And like cross section 1, cross section 4 is an upstream cross section where the fluid lines are approximately parallel and the cross section is fully effective. In general, fluid contraction occurs over a short distance, fluid expansion. Okay, let's review the defined ineffective area. Okay, what's the ineffective flow area? You know, when you want to model bridge or culvert in a study ridge, the area of the flow is decreased because the piers and abutment of the bridge decreases the effective flow area, and therefore HEC-RAS recommend you to use ineffective area in cross section 2 and 3. For example, this is cross section 2 and this is cross section 3, and you should use this area as ineffective flow area because in this case HEC-RAS does not use the whole area of cross section for the calculation of hydraulic properties and only use the remain section of this cross section. Okay, let me check the other values. Okay, contraction expansion losses like the cross section, as I told you before in the previous sections, it says that for subcritical flow contraction and expansion coefficients, for gradual transition, typical bridge sections, and abrupt transition that varies from 0 to lower 1 or 0.8. Okay, it says that for supercritical, let me check, okay, for supercritical. Okay, let me explain these values for supercritical in the later parts. For hydraulic computations through bridge, HEC-RAS have several available methods for computing losses through the bridge, including energy equation, I mean standard step method, momentum balance, Yarnell equation, and FHW-Visprue method. Okay, when you when you want to model a bridge in your river ridge, one of the most important problems is the calculation of losses due to existence of these structures. Okay, energy equation or a standard step method treats a bridge in the same manner as a natural cross section. Expect the area of bridge below the water surface is subtracted from the total area, and the width perimeter is increased where the water is contacted the bridge structure. Okay, the sequence of calculation starts with a standard step calculation from just downstream of the bridge. I mean, from cross section to cross section BD, from cross section BD to cross section BU near the upstream of the cross section, and from BU to cross section 3, and use energy equation for both cross section and estimate the losses from each breaches or sub-breaches. Okay, it says that the energy-based method requires Manning's n values for friction losses and contraction and expansion for transition losses. But momentum balance method use these equations for estimation of losses through the bridge. And these are the hydraulic parameters of both cross sections. And for, as I told you before, for energy equation, this equation again use momentum equations for between cross section 2 and BD, between BD and BU, and between BU and cross section 3, and then sum up all losses through the bridge. Okay, you can see the momentum balance between cross section BU and cross section BD, between cross section BU and between cross section 3. And in this and this equation there are some coefficients, for example CD, that is a drag coefficient, and in table 5.3 based on different pier shape you can find different drag coefficient. For example, when you want to model circular pier, you should use this value for drag coefficient, and for square noise piers you should use the value of 2 for CD. And the third equation is the Yarnell. Yarnell equation is an empirical equation that is used to predict the change in water surface and the losses of energy through the ridge. Okay, as you can see, based on this equation, Yarnell estimate the drop in water elevation from section 3 to cross section 2. Cross section 3 is located upper of the bridge, and the cross section of 2 is located in the downstream. And there are some coefficient and variables, for example K, Yarnell's pier shape coefficient, and in this table you can find, based on different pier shape, different Yarnell K coefficient values. For example, a square nose and tail, you can use 1.25, and for other pier shape you can find the suitable Yarnell K coefficient. Okay, V is velocity, alpha abstracted area of piers divided by the total abstracted area at section 2, omega ratio of velocity head to depth at section 2. which is these parameters are calculated in HEC-RAS model automatically. You can, and there is no need to do other tasks or issues. And the final method is, as I mentioned, FHW-WISPRO method. The low flow hydraulic computations of the Federal Highway Administration's WISPRO program has been adopted as an option for low flow hydraulic in HEC-RAS. Let me explain about low flow. In HEC-RAS, you can use two different flow types: low flow and pressurized flow. In low flow, the flow is through between the bridge and in free water surface, while in pressurized type, the bridge is completely submerged and some parts of the flow is through under the bridge and other parts flow over the bridge. Okay, WISPRO method computes the water surface profile through a bridge by solving again the energy equation. The method is an iterative solution performed from the exist cross-section to the approach cross-section, I mean cross-section 4. The energy balance is performed in steps from existing cross-section to the cross-section just downstream of the bridge, from cross-section 1 to 2. From just downstream to the bridge, to the inside of the bridge, from cross-section 2 to the cross-section BD, which is located inside the bridge, from BD to BU, and from BU to cross-section 3, and finally from cross-section 3 to approach cross-section, I mean cross-section 4. For each part or sub-bridge, the WISPRO method uses the energy equation like this, and repeated this equation and this calculation for different cross sections, and you can find different formula for different cross section. For example, for cross section 1 and 2 uses this equation for calculation of expansion loss, and from cross section 2 to 3 use this formula. And if you want to learn more detail about this formula, I recommend you to completely study the hydraulic reference manual of HEC-RAS and other related manuals. Okay, in high flow computations, for example, when the model is high, when the flow is in highly rate and flow tends to overtop from the bridge, the model uses automatically switch to pressurized flow computation. And in this part, there are different formula for simulating pressurized flow computation in HEC-RAS. For example, one of these formula is the FHW-A formula, which uses this equation for estimation of flow discharge through the bridge and other from the upper of a bridge. And there are some variables and hydraulic parameters. For example, when a model wants to calculate the total discharge through the bridge opening, use these equations, and this is the line profile of the location of a bridge. This is Y3, the water depth in cross section 3, the upstream of bridge. Y2 is the water depth in the downstream of bridge, and the Z is the distance between the riverbed to bridge, to top of the bridge. Okay, and there are some variable, for example, coefficient, drag coefficient, and it says that values for CD range from 0.27 to 0.5 with a typical value of 0.5 commonly used in practice. Also, for computation of drag coefficient, you can divide the water depth in cross-section 3 to Z parameter, and based on these values, you can find the suitable drag coefficient from this curve. Also, in the second case, when both the downstream and upstream side of the bridge are submerged, the standard flowing orifice equation is used. This equation is completely simple and like this. C is the coefficient of discharge for fully submerged pressure flow. Typical value C is 0.8, and H is the difference between the energy gradient elevation upstream and the water surface elevation downstream. And A is the net area of the bridge opening. And in this picture, you can completely see the situation of this case. As you can see, H is the difference between water surface or water depths in the downstream and the energy grid line elevation at the upstream of cross section 3. Okay, finally, for wave flow computation, as I told you, when the bridge is submerged, some parts of the flow through the some parts of discharge flow in opening parts, and some parts over top from the bridge. And in this section, the model automatically uses wave flow calculation in order to calculate discharge from upper parts of the bridge. Flow over the bridge and the roadway approaching the bridge is calculated using the standard wave equation. You can use CLH with the power of 3 divided 2. Q is the total flow over the wave. C coefficient discharge for wave flow. L effective length, and H difference energy upstream and road crest. And in these pictures, you can completely find the meaning of this approach. Okay, let me go to HEC-RAS environment and start to simulate HEC-RAS, simulate bridge modeling in HEC-RAS. Okay, in the previous section, we model a compound channel in HEC-RAS, and I want to load that project and start to enter bridge structures data. Okay, let me find the project. Okay, where is the Udemy? Okay, HEC-RAS 1D compound channel. Okay, you can use this process in natural rivers and man-made channels. Okay, this is the geometric data section, and you can find the plan and the location of cross sections. This is the profile plot. This is the cross section of upstream, and go to the downstream. Okay, let's assume that we want to model bridge structures between this cross section and this cross section. Cross section station 10.50 and 11.45. Okay, like a cross section, you should give a unique station for your structures. Okay, in the geometric data and in the left sidebar, there are different inline structure types. First of all, we want to select bridge culvert option to define the location and the shape of bridge, pier, and abutments. Okay, let me select bridge culverts. Okay, in this window, you can define different parts of a bridge. First of all, you should define deck roadway. I select road deckway and start to enter the required values and required parameters. Okay, let me to open the Word to explain more about how can we model bridge. Okay, let me to create a picture of bridge modeling. Okay, and let's assume that this is a natural river and we want to model bridge in this section. Okay, in this part. And these are the location of cross section. Let me to near the cross section. Okay, this is the cross section 2 and this is the cross section 1 and other cross section. Remember that if you want to model each structure, you should have a different cross section, and you can't different structures like this. It's not impossible in HEC-RAS or like this. You should define different and appropriate cross sections around upstream and downstream of the your structure. Okay, this is the plan, and I want to create a shape of the cross-sectional shape. Assume this is a cross section and we want to model a bridge in this section. First of all, you should model or define your deck or roadway. This is the roadway and the people are crossing over that. Okay, this is the road or the roadway. The roadway has 4 points. Point 1, point 2, upper the roadway, under the roadway, from the left side, down the elevation of, under the elevation of roadway, and the elevation, the upper elevation of roadway. Okay, and this is the length, and this is the length from left to right. Okay, we need to enter 4 main important points and the lengths. And this is the plan picture, and this is the cross-sectional schematic. Okay, first of all, it asks enter the difference. Okay, when you want to model a bridge, first of all, you should enter the distance between upstream cross section and the deck. What's the meaning of this parameter? Okay, let me move this parameter. It asks us to enter this value. As I told you, this value should be about 2 meters or 3 meter or a lower value. Okay, let me widen this shape. Okay, and this is the width of HEC, and this is the distance between the downstream of the bridge and the cross section located in the downstream of bridge. Okay, this is width and this is distance. Okay, first of all, we should define the station of bridge. First of all, go to the options and select bridge, add a bridge or culvert, and enter your desired river station. As I told you, I want to model a bridge between this cross section and this cross section station, and your cross section station should be between this value and this value. Okay. Okay, I select a river station of 11. Okay, it says that the distance between this cross section is about 100 meter. This is the upstream cross section and this is the downstream cross section. Okay, let me define the road deck parameters. Okay, excuse me, in order to avoid the size of this video, I stop this video in this time, and in the second part I will explain about how can we model deck roadway and other parameters.